Welcome back. Now on to Newton's second law. Newton's second law is basically the extension of Newton's first law. Newton's first law, the inertia law, we're talking about how if the forces are balanced, then the object is going to keep doing what it was doing. An outside, unbalanced external force is needed to change the state. If an object was at rest, to get it moving, you need an unbalanced force that will cause an acceleration. We call that force not just any force, we call it a net force, and sigma represents the addition, so this sigma F represents net force. It is not one force, it can be the addition, the difference of different forces. For example, if you have a pull to the right that is 45 newtons and pull to the left that is 40 newtons, you end up with a 45 minus 45 newtons to the right. Or if you have a downward force, let's say 100 newtons, and an upward force of say 80 newtons, then your net force is 20 newtons downward. So that is what net force is. So if there is an unbalanced part of a force or an external force that is exerted on an object, that means that the object is going to be accelerating. The wording of the formula, the way Newton wrote it, goes as follows. So you see how he wrote it as A equals. So when you have a fraction, then whatever is here, that is your directly proportional to. So acceleration for us is directly proportional to the net force. It also, notice how we have the vector sign here and the vector sign here. The object accelerates in the direction of the net force. Acceleration of an object that has a non-zero net force exerted on it will be directly proportional to that net force, and here, the downstairs, this is inversely proportional. So directly proportional upstairs, inversely proportional downstairs. So the wording of Newton's second law is acceleration of an object that is experiencing a non-zero net force is directly proportional to that net force and inversely proportional to its mass. So the heavier the object is, I should say, the more massive the object is, because remember, weight can be different and it can appear to be different from just mg. Acceleration is inversely proportional to mass, so the more massive the object is, the less susceptible it is to the change in motion. It's harder to accelerate it, and it is also harder to stop it if it's already moving. Directly proportional to the net force, inversely proportional to the mass of the object. A more conventional way to write down Newton's second law is force equals mass times acceleration. The big misconception is when people memorize it this way, they just say force equals mass times acceleration. What force? Net force. Now remember when we talked about force of gravity being the only force, and then we said it's equal to mg, and when gravity is the only force acting on the object, then g is the acceleration, which should make sense. If that is the only force acting on the object, that is the net force, and then your gravity being the net force produces the acceleration that exactly equals g, which is on Earth 9.8. In this worksheet, we have several situations, but before we go on to figuring out free body diagrams and combination of forces, let's practice. This practice reminds us that force, which is measured in newtons, takes mass times acceleration. And mass needs to be in kilograms and acceleration needs to be in meters per second squared. So if you remember, it's 1,000 grams in a kilogram, so that 400 grams you will have to divide by 1,000. That's how many grams there are in a kilogram, and you're going to end up with 0.4 kilograms. So the question here is, what is the net force required to accelerate this 400 grams or 0.4 kilograms object to the rate of 2 meters per second squared? That's going to be 0.8 newtons, the net force. And again, it could be, if I look at my box, I could be pointing with 1.8 newtons this way and only with 1 this way, and then we're going to end up with the net force being 0.8 newtons to the right, and that object will accelerate with 2 meters per second squared to the right. Next question, we have net force declared to be equal to 25 newtons, and the mass, again I have to divide by 1,000 because it's 500 grams, the mass is 0.5 kilograms. So if that net force Again, 25 newtons, what could it be? It could be a box is being pulled to the left with 75 newtons and only 50 this way. That way we're going to end up with your net force being 25 to the left, 25 newtons to the left. Acceleration in this case is going to be net force divided by mass. Again, mass needs to be in kilograms. Do not divide by 500. So it's going to be 25 divided by 0.5. That's going to be 50 meters per second squared. And C, we need to find mass in C. So net force is mass times acceleration, from where mass is going to be net force divided by acceleration. So it's going to be 1.5 divided by 3. That's going to be 0.5 kilograms. And you can keep it this way. You don't have to say this 500 grams. In the next few examples, we're going to look at the exact forces that are acting on the object, and we're going to determine the net force resulting from those forces. So we have a 15 kilogram box, mass is 15 kilograms, so I can figure out, just for practice, 147 newtons. We had an example like that. So I have force of gravity and a matching normal force. Both of them are going to be 147 newtons, 147 newtons. So vertically, I can say net force of vertical equals 0. They're balanced out. So the object is not going to be, our box is not going to be accelerating up or down. We have a 45 Newton force to the right and 20 Newton force to the left. So what is our net force in this x direction? That will be 45 minus 20. That is 25 newtons. And it's going to the right. So then acceleration of our box is going also to be to the right in the direction of the net force. And to figure out its magnitude, we're going to divide 25 by 15. That is like 5/3. So that is about 1.7 meters per second squared. And it's going to be to the right in the direction of the bigger force. In example 2, it's very similar. It again is a box on the ground and it's being pulled with just one force, but there's force of friction in the opposite direction. It's a 12 kilogram box, so I'm going to have force of gravity, which is 12 times 9.8, 117.6, so I'm just going to say 118 newtons. And normal force is going to match it exactly. And then we have a force of pull. I'm going to pull it to the right. Force of friction is 22 newtons. Then net force, again, net force in the y direction vertically is 0, but the net force in the x direction is going to be 25 minus 22. And we're not going to add x and y directions because they're not along the same line. So that's going to be 3 newtons. 3 newtons of net force, which will lead to acceleration that equals to 3 divided by 12, and that's 0.25 meters per second squared in the direction of the pull, and I drew it to the right. Example 3 is going to be very similar, only it's going to be pulled to the left, and force of friction is going to be a question mark. Force of gravity is going to be 58, which is mass times 9.8, which is g, 568 newtons, 568.4. I'm just going to round it up. Normal force is going to be equal to gravity because it's just flat on the ground and everything is balanced out in the y direction, but in the x direction. So we have a net force in the x direction, which is force of pull minus force of friction. And force of pull is 300, and force of friction is what I'm looking for. And I also know that that will give us an acceleration. An acceleration is 1.25. 300 minus force of friction equals 58 times 1.25, which is 72.5. So 72.5 newtons is the difference between friction and force of pull. So you can round it up to 73 if you want to, just keep it at 72.5, that's fine. So 300 minus 72.5 is going to give us 227.5 newtons. will be the force of friction. In question 4, you have a similar example, but now you're figuring out the force of pull. We've had 45 kilograms before, so you probably remember it's 441 newtons of force of gravity. Normal force is also going to be equal to that. Force of pull in this case is a question mark, and force of friction is given to us as 154 newtons. And we also know that because force of pull in this case, just like before, is greater than force of friction, I can say that net force in the x direction is going to be force of pull minus force of friction, and it's going to be equal to mass times acceleration. Mass is 45, acceleration is 2.5. If before we did a subtraction, so we're going to add 45 times acceleration to force of friction. We got 266.5, so force of pull in this case is 266.5 newtons. Example 5 has 3 things in it. And if you remember how we did force of gravity in the previous video, we talked about how during the fall with a terminal velocity, it's terminal velocity because there's no more acceleration. So force of gravity and force of air resistance are equal. Force of gravity being mg and being 75 times 9.8, that gets us 735 newtons. And because it's falling at a terminal velocity, that means acceleration equals 0. That means net force equals 0, which means whether I go mg minus or force of gravity minus force of air, it's 0, or force of air minus mg is equal to 0. So because they are balancing each other out, that's how we know that there's no acceleration and it's terminal velocity. If we have a downward acceleration, that means that the downward force is greater. So force of gravity, I'm not going to change force of gravity. It's still 735 newtons of gravity because it's the same person. Air resistance is less. So if air resistance is less, I'm going to say 735 minus force of air, that's our net force, equals mass times acceleration. This is 75. This is 4.8, and it's downward. So I made the downward force, which is a force of gravity, greater than the upward force, which is the force of air resistance. So from here, force of air is going to be 735 minus 75 times 4.8. That gives us 375 newtons. And then the last example, we have an upward acceleration. If the acceleration is an upward direction, that means that force of gravity is now less than force of air resistance. So force of air, in this case, net force is going to be force of air minus mg, will be equal to mass times acceleration. Force of air is, again, what we're looking for. So force of air is going to be mg plus ma, and I'm going to just do this. I'm going to do 75, and I'm going to add 9.8 and 4.8. So together, that's like 75 times 14.6. It's going to be 1,095 newtons. There we go. That is the answer to the last problem on Newton's second law. If you have any questions, I will see you before or after school, but hopefully this was helpful. Keep learning.